Welcome back, everyone. As you can probably tell by this chapter, it's a lot of fun to see the new perspective, and more importantly, it lets you feel like we're diving into a deeper level of physics. I know I was real excited to cover it and relearn and familiarize myself with these concepts because it truly is a magnificent theory. And I think one of the coolest things is how we can see things that this question highlight. That being said, let's dive in. For part A, show that E dot B is relativistically invariant. Let me note here that invariant and conserved are often used a lot in physics, but we have to be careful with how we interpret them. Conserved means that a quantity is unchanged during a process. Conservation of energy. Before and after, energy needs to be the same. Invariant means that I am unchanged during a transformation. In this case, going from one frame to another. That's what we have to be looked out for, and that's where the definitions come in. So just be aware, they're close, they're very close, but they're kind of different. And that difference means a lot. So be aware of that. Same thing for part B, show that E squared minus C squared B squared is relativistically invariant. Note here again that E squared is E dot E and B squared is B dot B. So those squares, although they're nice, we definitely have more work to do. Part C, suppose that in one inertial system B equals 0, but E does not equal 0 at point P. Is it possible to find another system in which the electric field is 0 at P? Okay, well, we kind of saw a system where we had a B not 0 and a B, or B 0 and E not 0. Let's see if we can kind of manipulate that. We saw that a couple questions ago. What we need to know, well, if we're trying to show relativistically invariant, we need to know how the fields transform. So we have these component-wise by component-wise. There was a nice derivation of this in the book, and there's several other texts, especially from the Jackson branch of textbooks, and several other things posted on a physics research guide. Now I'm blanking. American Physics Paper Review, something like that. I'll post a link. But this treatment is very careful, and you have to be just aware of these transformation rules made very specific to which direction we're transforming in. So the concept might be shifted based on which way you're transforming. That being said, we know what EX bar to EX is, EY bar, EZ bar. So a lot of these things, as you might imagine, look like cross products for a reason. Similarly with B, Y, we end up switching what we call E and B and putting a plus sign, and then of course we have to have a factor C squared there. So a lot of the things we saw earlier coming back to us again. All right, moving on then. What we see first is that in A, the question is asking to show invariant that E dot B is equal to E bar dot B bar. Okay, that's what we're actually mathematically trying to show here. And it's easiest to start off with, if we start with the invariant product E dot B in a transformed frame, do we get out the untransformed coordinates? And let's see. The dot product is pretty straightforward. We like that. EX, BX, that's the easiest as we can get. Now for EY and BY in the bar system, we're going to have to be very careful. We got two brackets for it. Same thing with the Z components. Our goal now is just to let algebra run through and simplify this down. You notice how we have a gamma in every single bracket here. So the gamma squared comes from the Y's and the Z's. So we just factor that out. And now we're just left with the cross terms from the cross product. And we're going to have to go ahead and FOIL those and distribute in. So here, upon the foiling, we actually get something really cool. These cross terms here are what are going to end up vanishing and canceling out nicely. So I color coded in blue so you can see that they cancel out. The V's, or the V over C squared terms end up canceling. I thought that was so cool. And then we're left with a double team of YY, and then you got ZZ, ZZ, and YY. So both terms have a minus V naught squared on it, V naught squared. So we can factor out the double indices, EYY, BY, and then EZ, BZ. And we noticed that if we plugged in the ratio for gamma squared, that was just 1 minus v squared over c squared, and voila, you could factor out that term again, cancel, 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 and after cancellation, we were indeed left with exactly what we needed to show invariant. I thought that was so cool. And best part is there was no trickery to have to do here. This was just a direct proof based on definitions. So easy enough to deal with. And since we like that, let's continue on our journey. All right, so for part B then, well, we have to ask ourselves the same question. Does e squared minus c squared b squared equal e bar squared minus c squared b bar squared? Sorry. Again, we saw that the squares are a dot product, and of course it's easy to show that based on the transform field rules, taking a dot product yields something pretty quick. So just like we did in part A, plug in the transformation rules. We see that we get ex squared, the transform to ey squared, the transform ez squared. Since it's a dot product with itself, go ahead and factor that gamma out. To see the cross terms canceling again. We like to see that. Here we're going to have to be a little more careful with the bookkeeping since we need to now have the negative c squared b squared. Again, that b squared is also the dot product, so we get the bx bar term squared here, transform z or transform y, transform z. Again, we'll play the game of factoring out the gamma. Here I distribute the c to bx and to the gamma, just so we can kind of solidify this bracket with the foiling that we had to do. The reason why is because now we can distribute that c squared in and kind of knock out some components and cancel away kind of nice. You see that the blue term here cancel with the blue term and the e squared, and then the red term cancel with the red term from the e squared as well. So by taking their difference, what we see is that we get e squared x minus c squared bx. We factor out the gamma. We can plug in a multiple of 1 here from distributing, of course. Everything tends to work out, and let's let algebra ring through. And we see that once we do, everything with the gamma terms cancels down as we need it them to, and we can cancel after common factors. And of course, we get all the e terms here. All the b terms are multiplied by a c squared term after we kind of force the gammas in there. That's what the c squared divided by c squared was in the last slide. And now after that, you know that since you have the components of every vector, x, y, and z, all squared, that's just the same as a dot product. Of course, it's a dot product with itself. Therefore, we know we have e squared minus c squared b squared. So yes, invariance. That being said, the last part of this question was kind of tricky and it made us have to work a little bit. The answer is no. And for if b equals 0 in one system, then e squared minus c squared times b squared is positive. Since it is invariant, it must be positive in any system. Therefore, e cannot equal 0 in all systems. So that's what's cool about proving invariance, because now we can kind of shortcut little mind games like this. We can have a field of b that is 0 and 1 simply due to how we mark what's moving and what's not. And once we transition frames, we can see that b does exist in another frame. That being said, the e still has to exist too. Thank you, invariance, for showing that.